And that's how you learn how to know what the question is asking for, is by practicing the homework. Whereas, in other words, I guess what I'm trying to say is physics is not only, it's not really a memorization game, all right, like some subjects are, where it's just, if I just memorize all this stuff, I'll be fine. It's more of, here's like 4 or 5 big areas. Now we're going to have about 12 problems that we could do with each one of those areas to stump you. And so that's what makes it kind of hard. I think what I'll do is I'll just go through it, find a good test here. Of course, all the good students come back and pick up their tests. Those aren't any good. Let's try something. All right. This is not bad. These aren't bad. All right. Here's a pretty good one. Boy, R. Kelly did a pretty good job. All right, and some of you, on some of those questions, I'll get to it in a minute. Okay, now, first of all, now remember, each test is a little different, so I'm going to tell you the question I'm going to do. In fact, if you've got test D, then I'll be following right along with you all. But if you've got a different one, I'll wait for you to find which problem. This is one where we've got a light beam with a wavelength of 422 nanometers in a material, and its wavelength becomes 675 once it enters the air, 675 nanometers and then it said, what's the index of refraction for the material, and at what angle with the surface will the beam be totally reflected back in the material? See, this is one of those ones where you're going, oh, I recognize right away that this is critical angle and finding the index of refraction problem, which you can only do if you've done some of the homework and you're practiced at it. Otherwise, what you're doing is you're writing a bunch of Snell's law and a bunch of other stuff that doesn't pertain to the problem. So this problem is actually very simple, well, fairly simple. And if you know what you're doing. That's the way kind of physics is. If you don't know what you're doing, you can't fake it sometimes. And if you do, then it seems to be pretty straightforward. So here would be, for my numbers, here would be the index of refraction. That's where you'd find it. Okay? Some of you had that reversed. I'm like, nope. I think we made it pretty clear that the index of refraction can't be less than 1, or else you're being big trouble. Okay? Index of refraction can't be less than 1. All right. And then it says at what angle with the surface, this is critical angle, will it be totally reflected back in the material? That is asking about what the critical angle is. And the sine of the critical angle is equal to, this would be the n of the material, is equal to the n of air over the n of the material. Now, if you try to do that the other way, where you got the n of the material, the n of air, some of you are going, my calculator keeps saying this is an error. Well, yeah, it's going to say that when you try and do the inverse, because the sine always has to be what? Less than 1, right? So this came out to be then theta of the critical angle is actually the inverse of 422 over 620 over 675. And all right, the way the test was graded out of 80 points for this problem is worth 10 points total, 5 for each one of the things. If it was just a one question thingy, like which one was a one question thingy? Oh yeah, everybody's favorite problem, the one where you got a parallel beam of light containing 2 waves, 408 strikes a plain piece of glass. That's basically the Prism problem. That one was worth 10 by itself. And then everything else, if it had every A and B part, was just 5 points, okay, based on 5. All right. So the next problem was, this one caused people a lot of heartache too, because you didn't understand what the question was asking. And it says a 120 millihenry. All right, that's the other thing too. I think I said to you, I didn't mean to be snarky in the email, but I'm going to. You got to start really watching what a question's asking for, especially if you're going into the health sciences. We don't want to give somebody $1 million off the dosage and things like that. That would be a bad thing. Okay, so 120, so L, this is one with the millihertz, 120 times 10 to the negative 3, which is what millihertz means. Millihenries, sorry. There we go. Millihenries. And then it's got R is equal to 20. I think the numbers were all the same on this one. The only one where the numbers were different was on the wave equation, which we'll get to in a minute, too. And then it had a variable capacitor. And basically, it had a C1, which is equal to, again, you got to be careful, 0.11 times 10 to the negative 6 farads, microfarads, and C2 is equal to 0.4 times 10 to the negative 6 microfarads. Okay, and the question was this: what is the range of resonant frequencies possible? Well, FO is equal to 1 over 2 pi times the square root of LC. So again, this is one of those ones where, okay, I could go through and write down the formulas. I could have F equals 1 over 2 pi times the square root of LC. But if I don't know what L is, I don't know what C really stands for, and I don't know that this means resonant frequency, and I also don't know when things are at resonance. And I think we did a problem just like this in class. At resonance, which means then that XL equals XC. That was kind of key to the second half of that question. All right, so the range of frequencies, then you just had to do this twice. You had an F1, and you had an F2, F naught 2. And that would give you your range of frequencies. Just compute that thing twice. That's it. Putting in the right, see? Boom. Those kinds of mistakes you got to be careful with. All right, that I just made. Okay, then the second one, when connected to a 24-volt RMS source, what current flows at resonance? Well, the current that's going to flow at resonance, XL and XC, cancel each other out. So it's just this, V equals I, R. It was that simple. 24 equals I times your ohms times R. So you get 24 over, in my case, it's 24 over 20. Some of you had different numbers. You had like 6 volts, or you had different RMS number there and a different resistor. And then this one came out to be what, 1.2 amps, something like that. All right, so that's that one. Now, go on to the next grand page here. This is an object. Okay, the next one was the mirror equations. All right, and this one is a concave mirror. Most everyone got this one good. This one was pretty good. This is the concave mirror where an object is placed 15 centimeters from a concave mirror of a focal length of 20 centimeters. Again, some of you who were under test anxiety or whatever, you took your focal length and you divided it by 2. It's already given you the focal length. That's the radius of curvature you divide by 2 of the mirror to get your focal length. So I was like, oh no. They kind of messed that up. But anyway, it says, where is the image formed? And some of you just gave me behind the mirror. I gave you 2 points out of the 5 for that, but I wanted a number there too. So that's kind of misleading question there a little bit, I guess. But it says an object. So and basically this is this. It's 1 over F equals 1 over DO plus 1 over DI. And if everything, one of the nice things about mirror equations is if everything in there is centimeters, which we ran into a problem when we were talking about that projector, though. You had to convert that one to meters. If you just leave everything the same, then you got it. Then you got 1 over 20 equals 1 over the distance of the object was 1 over 15 plus 1 over DI. And this would be 3 over 60. Minus 4 over 60 equals 1 over DI, which equals 1 over 60, negative 1 over 60. That's 1 over DI. That's not DI. Some of you told me that was DI. Got one last thing to do. Flip it over. DI equals negative 60 centimeters, which means it's behind the mirror, and its magnification then, its magnification would be plus 4. And it's actually upright, which makes, remember we talked about that? This would be like a makeup mirror, putting something in front of a makeup mirror, because makeup mirrors have really large radiuses of curvature, and so the focal length is really long, and so when you put your face is between the focal length and the makeup mirror, so therefore it's magnified a little bit. Right? So this one was magnified because the magnification equation is negative 60 over 15, which came out to be positive 4. Okay. So how tall would it be? Be 4 times the height, initial height, the magnified height, HI, height of the image is HO times 4. HO times M, so it would be 16 centimeters. Some of you converted the whole thing to meters and stuff, and that was fine. As long as it came out to be 0.16, that's okay. And 0.6, negative 0.6. All right. Now, convex mirror. Half of you lost some points on this because you were going, convex mirror, F equals 30 centimeters. And some of you, I went, yay, they did it. They did it right. If it's convex, what do we know about the focal length? Negative. It's negative, okay? So focal length is negative. So on the one with the convex mirror, you've got 1 over F equals 1 over 24 plus 1 over DI. So again, we've got to do the same thing again. We've got to find this image distance. And we've got negative 30 minus 1 over 24. And so we've got 1 over, that equals 1 over DI. This would be negative 4 over 120. And minus 5 over 120. I think that's right. Gives me negative 9 over 120, which divide by 3, I get 3 over 40. Yeah, 13.3. So DI is equal to negative 13.3 centimeters. And then once again, it says, where is the image formed? Well, it's going to be formed behind. And usually, not usually, always in a convex mirror, it's going to be a smaller image and it's going to be upright. In this case, how tall is it? It came out to be like 1.1. It was 2 centimeters tall. Now it's 1.1 because the magnification is equal to negative 13.3 over 24. So you take that, multiply it by 2, times 2, times 2. Basically, you're taking negative 13.3 over 12, and that gives you about 1.1 centimeters. It's positive. Because it's negative, so that's positive. There you go. So it's upright, and yeah, I didn't ask you I just asked you how tall it was. I didn't ask you if it was right side up or anything like that. Okay, now, an AC voltage, revoltage, everybody's favorite problem. Okay, and some of you, I dinged you for not changing to radians, but I only took like 1 point off for not changing radians. But then some of you, I accused you of bad algebra or bad trig. Okay, and I'll show you what I mean when we get to that part, because that's what some of you missed. All righty, let's do this. Here it is. All right, mine is one, it says 120 volts. Some of you had one that only said like 6 volts or something like that. All right, so here's my equation. It says this. It says V, there's a much better thing. V equals V naught times the sine of 2 pi times the frequency times t. Okay? And I'll get to, and so the VRMS of this is equal to V naught divided by the square root of 2. And the amplitude of the thing, V naught is also known as the amplitude. Okay. So, this is equal to 120 divided by the square root of 2, which I can't remember what, 85, I think it was. 84 point something. 0.8 volts, or 85 volts. I took.
Is the 120 given?
Yeah.
Because mine says 140.
Yeah. What's that?
Mine says 140, but you put 120 over.
Oh, that's because I've just been grading 400 others, but it's 140 over the square root of 2. Yeah. Okay, then the second question is, what is the instantaneous voltage at 7 milliseconds? Not 7 seconds, 7 milliseconds. And here's how you do that. And here's where some of you lost 1 point. Some of you went, oh, well, that's easy. I'll just go V equals 120 times 2 pi. And the frequency of this thing was 60 hertz. Some of you had the frequency was 50 hertz. Some of you, your test went to Europe or Asia on us. But anyway, 2 pi times 60 times 7 times 10 to the negative 3 seconds. Put your calculator on radians. All right? And when you do that, you came out with something. I don't know what it was. Now, on the next part, it said this. It says, when will the voltage be 77 volts? So on part C, here's what you did. You went, oh, well, 77 equals 120, or whatever yours was. It was 120 times the sine of, now all of this is in parentheses, 2 pi times 60 times t. Okay? Now, so you take the inverse sine of 77 over 120 equals 2 pi times 60 times t. Okay? Some of you took 120 over the sine of 2, did this. You said 77 over 120 times the sine of 2 pi f, like this, equals t. Can't do that. Illegal move. Because that t is inside, he's part of that angle. Okay? So that's an illegal move. All right. Now you can divide it by 2 pi times 60. And that'll give you your t. Again, you have to take the inverse sine in radians. Some of you did it beautifully. You just had it in degrees. All right. Now, yeah, these last 3 problems were everybody's favorites. This is where most of us kind of hit some heavy rolls here a little bit. Not too heavy. All right, now we've got a slide projector. And I apologize to those of you who had test number D. I didn't realize I gave you absolutely no room to work this problem. Some of you chose to work it on the back, or you adapted, overcame, and adjusted just fine. But for the most part, all right, now here. And remember, when you're taking an exam, I'm a pretty liberal guy. If you're stuck on what it's asking, I'll tell you what it's asking. I may not tell you how to do it, but I'll at least tell you what it's asking now, or what the problem is saying. And I think we did this on this one. It says a slide projector is designed with its lens 6 meters from the screen. Okay, so that means the distance of the object, or the distance of the image, is going to be 6 meters. Okay, so for the slide projector problem, you had DI is equal to 6.0 meters. Okay? And the distance of the image is what we're asked to find. And the way we can find the distance of the image is, first of all, they told us that the height of the image, the height of the object, was 0.025 meters, and the height of the image was 1.5 meters. That's what that silly thing was saying. Okay? And so then you go, oh, all right, so my magnification then is equal to height of the image over the height of the object. So the magnification is equal to 1.5 over 0.025 is equal to 60. Okay, so that's my magnification. So then I also know that my magnification is equal to the negative of di over do. Okay? And since di was behind the lens, it's negative. And so this is 60 divided by is that right? Yeah. Oh, sorry. I'm trying to do this all in one step. Let's just do di over do. And so I've got do is equal, thank you, is equal to di. Remember, I don't take instructions on algebra well from the crowd. For some reason, I just can't do it that way. So there we go. And so I've got do is equal to the distance of the image was 60 over 6 meters over 60. So this would be 0.1 meters. All right. And then we also knew that we had to find is that what we were supposed to find? Oh, I'm sorry. Yeah, what's the object distance? There we go. There's the first 5 points. Whew. What's the focal length? Well, now that we know we can do 1 over f equals 1 over do plus 1 over negative di. 1 over di, where di was actually equal to negative 6, actually. I should have put this because it's behind. So that's why some of you got 10.2 on this down here instead of 9.8. 9.8 was actually the $1 million answer, but that's okay. I let it go either way. And so you wind up with this. You wind up with 1 over 0.1 minus 1 over 6 and you just take it from there. So you wind up with the focal length is actually equal to like 9.8 centimeters. And then the power of it is also known as diopters, is equal to 1 over f in meters. So it's 1 over 0.98, and that came out to be like 10.2. Okay. All right. Now, last one. Very, very last one. A parallel light. All right, some of you, this was a prism problem, and we did the problem just like this in the book in class, where we were finding the difference in the angle between a light that hits on two ends of the spectrum so that it separates out. That's that diffraction pattern that we'll talk about here on this next chapter. Oh, we're not going to have time to move on to the next chapter. That's okay. All right. It says a parallel light beam containing two wavelengths. Lambda 1 equals 480. And some of you didn't know what this thing was asking. It's asking to do Snell's law twice. Is basically what this thing was saying. Just do Snell's law twice. Okay? And saying a parallel light beam containing two light waves strikes a plane piece of glass at an angle of incidence of 60 degrees. Okay, first of all, I will admit a little bit that this is possibly poorly worded because it was coming from air and hitting the glass. Is the assumption. It's making an assumption here. All right. Some of you asked and said, "Do they mean from glass?" I said, "Yeah, That's what it means. All right, so now we've got two different things coming. So a parallel so we got the two different spectrums of looks like we're going from red to blue light here. Strikes a plain piece of glass at an angle of 60 degrees. Okay, the index of refraction of the glass is 1 for the 1 and 1.467. So basically what they're doing is you do it for lambda equals 480 nanometers, and you do it for lambda equals 700 nanometers, or whatever you had. Some of the numbers changed to protect the innocent there. Okay? And N1 is equal to 1.00 for the air. And 1 over here is equal to 1.00 for the air. And N2 is equal for this one was 1.438, 1.483. N2 it was 1.487, maybe 76. All right. And so here's what we did. So you went, okay, N1 sine of 60 equals 1.483 sine of theta 2. And then the same thing over here. N1 sine of 60 equals 1.476 sine of theta 2 for this one. And so theta 2, doing a little shorthand here real quick, is equal to sine of 60 over 1.483. Okay, some of you got that far. And then you went on to do this. Theta 2, I'm going to make this theta 2 prime, is equal to the sine of 60 over the inverse. Inverse sine. There we go. And then what we were supposed to do at the end was find the delta theta is equal to theta 2 prime minus theta. Minus theta 2. That's what that problem's asking you to do. If you did all that, I didn't care what your number was. If you got that, I didn't, I mean, because the answer key said, you know, if you came up with 0.196 and the answer key said 0.203, I was like, close enough. If you did all that, you're in the ballpark. I mean, you did it. Okay. All right. Okay. That should, yeah. Let's make it a wrap. I don't want to get into waves. Well, sorry about that.